Hey guys, in this video we're going to talk a little bit about Le Chatelier's principle. Alright, so this is a concept in equilibrium where if you have a system which has already achieved equilibrium, like it's happy, it's satisfied, everything's good, and then you make a change to the system will respond in a way that will restore it back to equilibrium. Okay, so I picked this right here as an example, this reaction, the formation of ammonia. I have no idea what the equilibrium constant is for this, but let's go ahead and write the equilibrium expression, and then I'll just make up a value for it, just for the sake of argument. Let's see, NH3 squared, because of the 2, over N2 to the first power, because remember, products over reactants, and then hydrogen to the third power. Great. Let's pretend that the value of this equilibrium constant is, I don't know, 1,200 or something like that. Okay? No idea what it actually is supposed to be. And let us furthermore suppose that the system is already at equilibrium. All right, now I have no idea what these particular molarities are going to be that makes the system be at equilibrium. So give me a moment and I'll make up some numbers real quick. All right, here's some numbers I made up. We're going to find out real quick if this is indeed equilibrium by plugging in the numbers. And if it all multiplies and divides out to this value, then we're at equilibrium. All right, let's see what happens. Hey, looks like I did my math right. The system is indeed at equilibrium. This is a combination of concentrations that would cause the system to be at equilibrium, meaning stable. You'd have now the same rate of forward reaction as you have reverse reaction. Great, that's all anyone really wanted. Okay, now, what if you're looking at this reaction vessel of just the stable equilibrium, and you go ahead and dump in a whole bunch of hydrogen. You just these are gases, so dump in is probably the wrong word, but you've got like a gas syringe and you squeeze in a whole bunch of hydrogen. All right, let's say that you put in so much hydrogen that now this concentration is 1. 10 times larger than it should be. All right, well, let's see what that does. This would now be 1.2, which is decidedly less than 1,200. So the system is not good with this, right? Now, if you think about mathematically what just happened, right? 1.2 is less than 1,200. One of two things, maybe both things, are true here. Either the denominator is too big, okay, or the numerator is too small. And so the system has to mathematically try and fix that, right? In order to get this all to multiply out to give me 1,200, the system has to decrease the size of the numbers in the denominator and or increase the size of the number in the numerator. All right, now what that means, practically speaking, then, is this. The forwards reaction has to speed up. We will restore equilibrium with some different set of values. I'm not going to bother to calculate exactly what those are for the purposes of this video, but in order to restore equilibrium, the forwards reaction has to speed up. We've got to get rid of stuff over here on the reactant side and make more stuff on the right side. All right, so what would this look like as a question? Meaning, like, what would they ask you in, say, the textbook or in a test or something? How would they phrase it, right? Okay, so here's how it would be phrased, something along these lines. The following system, as you see before you, is at equilibrium. Hydrogen is added to the reaction vessel. how is the system going to restore equilibrium? Or what is the effect upon the concentration of nitrogen, or the effect on the concentration of ammonia, or something like that? Okay, all right. In general, then, here's what we're going to see. The system will shift to fix whatever the disturbance is, right? The disturbance in question was adding a bunch of hydrogen. All right, if we have too much on the left side, then the reaction shifts to the right. All right, that's our vocabulary, shifts right, which means that the nitrogen concentration is going to go down. The extra hydrogen that we added into the vessel is going to react with the nitrogen that's still in the vessel, right, and produce more ammonia. So the nitrogen concentration will go down, and the ammonia concentration is going to go up. Now, if you're like, what will happen to the hydrogen concentration? I mean, it's going to go down from the absurd levels that it briefly is after we dump a whole bunch of it into the reaction vessel. It will probably never get back down to this original amount that represented what equilibrium was, right? The new equilibrium position is going to be different, and it will include a larger amount of hydrogen than we had before. Okay, nonetheless, we would say the reaction shifts right because it's going to reduce the amount of stuff on the left side, giving us less nitrogen than we had before and more ammonia than we had before. All right, what are some other changes that we might make here? If they say something like this, what if you remove ammonia? Now, you might be wondering, how would you remove the ammonia? That's a question that we're going to not worry about, but there are things called chemical scrubbers, right, which are going to react with it and remove it from the system. In this particular case, that could be something like, throw in some HCl gas, and that will precipitate the ammonia as ammonium chloride. Okay, great. That's a valid way to do it. Don't worry too much about all those words I just said about, adding in HCl. It doesn't matter. If we remove ammonia, now there's too little on the right side. Again, this would shift right. And that means that the amount of nitrogen will decrease and the amount of hydrogen will decrease, right? If I am removing something from the system has to try and make more of it. So it will shift towards wherever the deficiency is. Okay, let's look at one other possibility here. Sometimes a reaction is endothermic or exothermic, and changing the temperature, while it doesn't actually affect the concentration of any of the various ingredients in your equilibrium equation, changing the temperature will shift the position of the equilibrium based on whether heat is a product or effectively a reactant, okay? All right, now, if you're wondering how does it do that if it doesn't change any of these numbers, changing the temperature actually changes the equilibrium constant. That is math that I'm not getting into in this video, but you would definitely see it in like an AP chemistry class. Changing the temperature changes the value of the equilibrium constant, and so thus it can change the position of that equilibrium. For this reaction, it is an exothermic reaction, right? That's what that negative sign means. Okay, so that means that if I wrote heat in my equation here, it would be technically a product. Heat is produced by this reaction. All right? So that means the following. In response to the question, what if you raise the temperature? Right? In response to that question, what we would say is, all right, if heat is a product and I raise the temperature of the reaction vessel, that's like dumping in a bunch of stuff on the right side. All right, so I want you to maybe pause the video for a moment and think about what would that do, right? What happened when we dumped in a whole bunch of hydrogen, right? How did the system respond in that case? So what does that mean about if I dump in a whole bunch of heat? Okay, so now that you've thought about it, okay, adding extra stuff on the right side would shift the equilibrium to the left. All right, so which that's consistent with everything else that we've said about how Le Chatelier's principle works. If I add something, the system will try to remove the excess that I have added. If I remove something, then it's going to try to fill in the hole, right, where I removed something from it. All right. Since heat is a product, adding heat will shift the reaction to the left. So that would mean that the the nitrogen would go up, hydrogen would go up, and the ammonia would go down. So yeah, that's one example. Let's take a look at another one, just for practice. All right, this time we're going to consider a KSP type reaction, right, where it's a solubility product, right? I'm going to start by actually writing that KSP expression because it's kind of important for answering some of these questions over here. Something only is going to, adding a material, a substance, is only going to affect the position of the equilibrium if it appears in the equilibrium expression. All right. So let's see. It would be Pb 2 plus times Cl minus squared. Great. All right. Now let's answer the questions. How does the system respond if the temperature is increased? Over here it says the enthalpy is positive 4.6 kilojoules. That's an endothermic reaction. That means that we have to add heat to get the reaction going. So heat is a reactant, essentially. All right. Increasing the temperature would shift the reaction. If you said to the right, you are correct, right? So this would shift right. Again, what shifting right would mean is we would get more lead and more chloride produced, right? The concentrations of both of those things would go up. All right, second one, NaCl is added to it. Na plus is irrelevant. That's not part of this, okay? On the other hand, the other half of that, the chloride's right here, right? Right there. So if I add more chloride, that is going to disturb the equilibrium. So if I dump in a whole bunch of stuff right here, the reaction is going to shift left. So we would produce more precipitate, and the lead concentration would go down. Okay, so shifts left. Related to that one, there's the possibility that they would give you something completely unimportant, right? If I said NaNO3 is added, sodium, not in there. Nitrate, also not in there. And so that wouldn't affect the equilibrium at all. All right, last one. Solid PbCl2 is added. Okay, this one is at least a little bit tricky, and here's why. If you look at the equation, you say, there, I found it. There's the PbCl2. It's on the left side. So the reaction shifts to the, hang on a minute. I don't see any PbCl2 in the KSP expression. Well, that's because it's a solid. Solids and liquids don't go in the equilibrium expression. That means it doesn't matter how much of this stuff I add, it actually will not shift the position of the equilibrium at all. So this would in fact be no change. All right, so for any substance that you add, it's only going to shift the equilibrium if that substance has a component that appears somewhere in the equilibrium expression. All right, I hope that's good enough. See you guys in next class.